everyone. So today we are going to continue to talk about this build make more part 3 here. And actually I finished this lecture about 2 weeks ago, so maybe I cannot remember everything about this lecture. So let's just try and see if I still remember something and try to explain it. Okay, so basically for this lecture, we have two problems need to solve. First one is the initial loss. As we see in the previous lecture, our initial loss is really high and we need to spend about like thousands of steps to make the loss to a lower make to a lower loss, and which means that we wasted a lot of time and calculation to let the initial loss go to the lower part. Okay, and there we have another problem is we want to fix the saturated tonnage. What this means that when the output of tonnage is near 1 or -1, its local derivative will be nearly 0. And when the output is nearly 0 and its local derivative is 1. This which means that the gradient passed by backward migration will only decrease. And if the output of tanh is near 1 or 0, and the gradient is destroyed when past tanh. And this is a problem we want to solve. Okay, and how do we solve this? So basically, for fix the initial loss, we introduce this thing called a timing init, and I won't go into that. So you can just set the paper and let and to know how this numbers come from. Yeah, and to fix the saturated tangent, we introduce this batch normalization. So actually, we want the input of tangent to be roughly Gaussian to make good use of tangent, which means that tangent neuron will be more effective. And so basically what batch normalization does is we just move the distribution to Gaussian. Okay, and there are some of the benefits. For example, stable training because of the jitter works. Its kind of regularization works quite well, which means that instead of directly moving it to Gaussian, moving the input distribution to Gaussian, we also add W and X, W and B, to make the distribution can be like can be trained another way. Yeah, I will show you later in the code. Okay. Yeah, it's just like here. Uh, okay. And after we introduce this batch normalization, how do we inference? So we will catch the batch normalization mean and standard deviation when running, and we use them for inference single input. And there's another point that the bias before the batch normalization becomes useless because we already use this another layer we will show to do this work. Yeah, and we want the batch normalization be sprinkled across neural net and place it after layers with multiplication. Okay, so basically this is what this lecture do, and now we're going to the code. Okay, so for here it's still the same here, like the previous one. And here we can see that. Or here is there we times the 5 over 3 is because of the we are trying to initialize the data of this layer. Yeah, we don't want it to be this is what we call the timing unit here. And for here, why we're going to time 0.01 is because we want it to be more like uniform distribution. Yeah. actually these things are solved when we have batch norm here. And you can see that we have this Bn gain and Bn bias. And we will use them to be our batch norm parameter. Okay, and we also have this running here to calculate the average and standard deviation here. Okay, so let's just go into the code here. Here you can see that for this linear layer is because we want to we are going to do batch normalization. And why we don't need this B1 here is because in batch normalization we're going to subtract all of them by the average. And the average is just this B. Is that right? Let me think. Yeah, it's because that you can think that for every input we add this B1, but their average won't change. So this B1 is then useless. Okay. And so here we also have this we just subtract by the mean and add this bias here. And here our running average is just going to calculate the average of the whole training data set by slowly update it. Okay. And here the hidden layer is still the same. Yeah. And yeah, and here is still the same. These are all same as last lecture. So basically what we do is just add this batch normalization layer to make our input to become more Gaussian-like. And it will activate the 10H layer much better and can mediate the gradient disappear problem. Okay. So you can see that for this loss here, we won't have this like hockey-like shape because we already initialized the parameter at the start, like here, uh, just based on the Chi-Min initialization, the number. Yeah, so you can have this result. And and training. Yeah, so because when we build this batch normalization, oh yeah, we won't need this step anymore. It's because that we now use this running to calculate the mean and standard. But if we didn't do that and we want to inference, we need this to calculate the whole training set mean and standard, and then we get the global mean and global standard deviation. Then we can do inference. But now for here we just use this running here. Okay, so yeah, we can get a result. And you can see that when we add this Chi-Min init from the original and add this Chi-Min init and add batch normalization layer, the result doesn't change a lot. This is because that, according to Andre, he said, is because like our model now just pick the previous three characters to predict next character. It is the bottleneck is not the batch normalization, it's the context of we look. So maybe we need to look more further before, for example, maybe from the first character instead of just looking the previous three ones. Okay. And for the second half of his lecture, he summary of the things we just told, and he tried to PyTorchify the model. So let's just go into the code. Okay, so here for this class linear, we have this fan in, fan out means the input and output dimension, and the bias equals true. Means that for uh, if we want to have the if we don't have this batch normalization, we need this B layer, right? Just as the last lecture. And this call means that we can just call the layer just like something like this. Yeah, and we will do this x times self-dot weight and add bias if we have bias. And we also define the parameters to collect all the parameters because when we do backpropagation, we need to turn on all of these parameters gradient to true. And for this batch normalization, we have this momentum and its trending here, and also have this epsilon. And we will see below here. Like this is just the uh, parameter we decided to update how fast to update our running mean and running variance. Yeah. Okay. And yeah, and this gamma and beta is just the shift and the growth. Just like the W AX plus B is A and it's gamma X plus beta. Yeah. You can see where can I see? Gamma, gamma, gamma. Oh yeah, here. Okay, so this is trained with backpropagation. Okay, yeah, and for 10H is still 10H. And now we can just build these layers here. And because we added this batch normalization here, it means that we don't need the bias, so we just turn all the false here. And for each linear layer, we add batch normalization at the end. Also the last layer. But you just need to mention need to like set the input to the right value. Okay, so yeah, I don't think this really did anything. Just make less confident for a next layer to make our output more smooth. Yeah, and this is for all the layers. We just turn on the gradient equals to true. Okay, so yeah, this is just all the definition, and now we're going to the ending process. So for the steps, we create the mini batch here, and we just go through all of the layers here. Yeah, because you can see that of layer one by one, and then we calculate the loss. And from the loss, we do this backward. Yeah, and we need to set the grad to 0 here. Okay, so we update here this line, and we also set the learning rate here, and we also track stat here. Okay, yeah, I think that is all. So let me check by what does gamma actually do. Okay, here. Okay, here. This one. This is also a trainable parameter here. Okay. So let's see the result. And also in this lecture, he introduced some diagnostic tools to check if your model is working well or not. For example, we don't want this activation maybe to uh, polarize, maybe to near 1 or 2 near 0. Yeah, something like that. And I just forgot how this data's meaning. So maybe if you guys know, can just put in the comments, or maybe if I come up with, because I think this is not a lot important here. Maybe it's still important, but not that important. And what I remember most is that we need to keep the line here, keep our ratio. The ratio is the gradient versus data ratio here. Once we keep them uh, at the 0.001 here, this is the, like, you will think that this is robust. Okay, so yeah, I think that is all. And now we want to evaluate our new newly built model, like hypertrophied model. So we need to turn this training into false, then we can uh, inference them. So we just also do the forward pass here, and but instead we don't do log entropy, regular entropy here. We use softmax here, and also use multimonial to sample it. Yeah, and this is all the just mentioned here. Just mentioned as like last lecture, just to make sure you need to turn this layer training to false, because I forgot and I was thinking that the code had some problem. Yeah. Okay, and let's think if there's anything I want to say more. Hmm. Yeah, I don't think so. Okay, yeah. So just to like wrap up, we need to know how batch normalization works and how to using our neural network. And then we PyTorchify the code and wrap up into modules. And we also know that the diagnostic tools to understand is a good state is in good state dynamically. Yeah, and those are the takeaways for this lecture. Okay, see you next time.